Okay, yeah, microphone works. So, good morning. I'm Jonathan Müller. I'm a software engineer at ThinkCell, and I'm here to give a very incomplete guide to C++ object lifetimes, as it turns out, because this topic is incredibly complicated, and even the C++ standard is wrong. So, we're just gonna get started a little bit here. So, it's a guide about object lifetime. So, the obvious question is, what are objects and what is lifetime? Objects are fundamental in C++. This is a quote from the standard. We're going to see it also a lot. Intro.object, paragraph 1. The constructs in a C++ program create, destroy, refer to, access, and manipulate objects. So everything you do in a C++ program is you change objects in some way. And by objects, the C++ standard doesn't mean objects in the term object-oriented. It's a term of art from the C++ standard. And to understand that, we need to understand three other things. The first is storage, the second is value, and the third is type. So let's begin with storage. The fundamental storage unit is a byte, and then the memory is just a sequence of bytes which have a unique address. So here's some memory, we've got some bytes, and each of those bytes contain a specific configuration of bits. Here I've highlighted the one that is OX41, right? It's just some byte that contains some bits. And that is storage. Now value is about the meaning of OX41. We just have a byte, it has some bits, what does it mean? It could be an 8-bit integer 65. And then it has the value 65. It could be the character uppercase A. It could be the start of the string that begins with uppercase A, or some other character in the middle of the string. It couldn't actually be something on its own, but just part of the 32-bit integer, and you have to look at the surrounding bytes in order to figure out what it means, and so on. There are very different ways of figuring that out. So, elements of programming says that a datum is a finite sequence of zeros and ones, and then if we interpret it in a particular way, that is a value. So we've just got a sequence of bits, and then we have some interpretation, like this is an 8-bit unsigned integer, and then we get the value out of that byte. And now a type simply is this interpretation. So if the type unsigned char means that we take 1 byte of memory and we interpret it as an 8-bit unsigned integer. If we take int, we need to take 4 bytes and interpret them as a 32-bit 2's complement integer. And types can be more complex. For example, string means we take 24 bytes of memory and we interpret them as pointers to a null-terminated sequence of char. So now we have to follow and look at some more bytes in order to get the full value, a size and a capacity. And so a storage contains some datum. A value is the mathematical thing when you get an interpretation, and the type is that interpretation. And now an object is simply something that has a particular type, occupies a region of storage at some address, and contains a value. So here we've got a couple of objects. The first object is called x and has type int, and it currently stores the value 42. So it lives at some address where it occupies some bytes, and those bytes will, if interpreted as an int, will be 42. The second object is a float y. It currently stores 3.14, and then in the last statement we can change the value of the object. So we still have the object, we just change the bytes to know they store a different datum, which now represents 11. Now it's important to point out that, for example, functions aren't objects. Even though a function has some storage logically on your CPU, they are not objects in the terms of the C++ standard. So a function f isn't an object, but they can be implicitly converted to function pointers, which themselves can become objects. Right? So f isn't an object, but tf, which is a pointer to f, is an object. Similarly, references aren't objects. References are just aliases to other objects. So we've got an object x, and then we've got an alias for x called ref. And this isn't a new object, it's just an alias to refer to an existing object using another name. So those are objects. Now what is lifetime? Well, objects have properties, and one of those properties is the lifetime. And it's a pretty important property, because all other properties only really apply while an object is in its lifetime. And in particular, there are significant restrictions on the use before the lifetime has started and after the lifetime has ended. So it's pretty important to figure out when the lifetime of an object begins and ends. So at a very high level overview, this is sort of the life cycle of an object. Objects occupy storage, so the first step is always occupy some storage for the object. We then need to initialize the object. This is in quotes, we will see why later, and this starts the lifetime of the object. So now we've got an object whose lifetime has started. We can then freely use it. We can read its value, we can change its value, we can do whatever we want. Eventually, the object will be destroyed, and this will end the lifetime. And finally, if we don't want a memory leak, we then have to deallocate the storage. And this is a very high-level overview of what's going on, and we're going to look at many specific examples of how that works throughout the talk. Now, some terminology. The standard says that objects can be created. And this isn't an operation that actually starts the lifetime. It just means now we've got an object we can talk about like it's just like a declaration of a thing. We are going to have an object, and it will have a lifetime at some other point. It's not an operation that starts the lifetime. But confusingly, the standard says destroyed, which sort of is the opposite curve created, but this is actually the name for the operation that ends the lifetime. So I try to be careful and not say create to mean start the lifetime, and instead say start the lifetime, but it's the opposite of destroyed, so it slips through. Also to point out that lifetime is something the standard invented to describe semantics on the abstract machine. It has absolutely nothing to do with your CPU. Right? Your CPU doesn't care about lifetime. It's purely a terms of art for the C++ standard to define semantics. So with that, let's get started. And let's begin with the simplest way we can start lifetimes using variable declarations. Intro.object paragraph 1, an object is created by a definition. So here we've got a definition of a variable x, and as we will see, this will both create the object, allocate storage for it, and start the lifetime. So we can then use the object, and then at the closing brace it will be destroyed, which will end the lifetime and also deallocate the storage. To figure out when exactly the storage allocation and the lifetime starts, we have to look at a property which is called storage duration. So the storage duration is a property of an object that defines the minimal potential lifetime of the storage containing the object. And it depends on how we created it. And for definitions, there are 3 storage durations: static, thread, and automatic storage duration. So let's look at those. Automatic storage duration is the simplest ones. If you have a variable that's just in a block scope or parameter scope without any special keywords, it has automatic storage duration. And the storage essentially is allocated when we encounter the definition and then deallocated when the block ends. So here we've got our 2 objects, and as soon as control flow reaches those lines, we will allocate storage for them. Again, on the actual CPU, we will probably allocate storage before that, but this isn't about the CPU. This is about the model of the C++ abstract machine. So now we've got storage for A and B. We then enter another block, allocate storage for C, deallocate the storage at the closing brace, and then deallocate A and B when we reach the end of main. Static storage duration is variables that are in global scope using static or extern. And their storage duration is even simpler. Essentially, the storage exists all the time. So the storage is allocated sometime before the program starts and deallocated sometime after the program ends. So here we've got a whole bunch of global variables, one regular one with like static linkage, then one function local static, and then a declaration of a global inside a function. And all of those have static storage duration, which means their storage exists all the time. We don't have to worry about it. Related to that is thread local. So if you use thread local, they have thread storage duration, where static storage duration lifetime exists throughout the program. Thread local means throughout the thread, and there's also a copy for each thread. So when we have a variable with thread local storage, when we start main, we've got 1 copy of this for the main thread. And when we launch another thread, we will allocate another copy for that, start storage for that, and then when the thread is destroyed, we deallocate the copy. So this is storage duration. And it's important to point out that storage duration is not the same as the lifetime of an object. It's a superset, but not necessarily the same. The lifetime only starts after we've done 2 things. The first is we've allocated the storage, we've looked at that, and then we completed the initialization, if there is any. And only then do we start the lifetime, and these things generally happen at different times. The good news is for automatic storage duration, they don't. They happen at the same time. There are some terms and conditions that we will see later on, but in general, when we have a variable of automatic storage duration, when we allocate the storage, we also start the lifetime. For static and thread storage duration, it's incredibly complicated. Then we have to look at function local static versus global scope. We've got const in it, we've got dynamic initialization, nifty counters, the module dependency graph, inline variables. It's an entirely separate talk. Like I gave a 60-minute talk just about that. You can find that if you look on YouTube. I'm not going to go into that now. I would just say automatic storage duration. It's easy. Static and thread storage duration, watch another talk. So the standard says initialization, if any, is complete. Because in general, an object can have the lifetime start without a known value. So when we've got allocated storage, and the object has an indeterminate value until we do initialization, essentially. And so what this means is then when we got something like an int x, it has now constructor, we don't provide an initializer, then we're immediately done because we don't need to do initialization, so we start the lifetime with an indeterminate value. And if we then try to read from that value, we've got undefined behavior, because we're reading an indeterminate value. However, we can read it after the assignment. And the assignment in the third line is only okay because we already started the lifetime of an object. Right? The first line starts the lifetime of an object, which means that we can assign it. However, we cannot read it yet because we don't have a value. But if the first line didn't start the lifetime of the object, then even the assignment would be undefined behavior because we don't have an object to assign to. Right? So this is the idea. And this behavior is going to change in C++26. So instead of being undefined behavior line 2, it's now going to become erroneous. And erroneous is a new kind of behavior. It's sort of like undefined behavior, but the compiler is supposed to be less aggressive about it. So it's essentially, it's still an error to do it, but the compiler cannot optimize based on the assumption that it didn't happen. So it cannot eliminate branches based on that and things like that. Essentially, it's only allowed to like either give you an indeterminate value or like issue a diagnostic, but not do further optimization. So it's sort of a tamed down version of undefined behavior to have like less problems with that. And that concludes variable declarations. Are there any questions so far? Okay. So let's look at new and delete. An object is created by new expression. And then we've got a corresponding delete expression which destroys an object. So what we can do here is we can write new int. This will create the object, allocate storage for it, and start the lifetime. Because it will new both allocate storage, and because it also does initialization, it will also start the lifetime, because we did two of those things. We can then use the object. At the end, we can destroy it, which will end the lifetime and deallocate the storage. And note that there are two objects. One is the int on the heap, and the other one is the int pointer on the stack, which governs by the rule that we had before. It's also possible to create one with indeterminate values, right? So this does the lifetime with an indeterminate value. Reading it is undefined behavior, but assign to makes it fine. Exactly like that, like in the previous section, but we've got more control over when we do the initialization, when we do the destruction. So that is pretty straightforward. So something more interesting are level 2, temporary objects. An object is created when a temporary object is created, which is a tautology. So consider this code. We've got our function f, which takes an int reference. And then we call it with 42. Now 42 isn't an object. 42 is a value, right? It doesn't have a storage, it doesn't live anywhere, it's just the number 42. But references are aliases to objects. So we need some object in order to bind the reference to. So the call creates a temporary object. This process is called temporary materialization conversion, which is a great phrase for Hangman. And the standard says a PR value of type t can be converted to an x value of type t. This conversion initiates a temporary object of type t from the PR value by evaluating the PR value with the temporary object as its result object and produces an x value denoting the temporary object. These are a lot of sentences to mean when we need an object and we have a PR value, we create a temporary object initialized by that value. So right? This happens, for example, when we bind a reference to a PR value, as we see in the previous example. It also means when we do member access on a PR value. So when we want to call a member function, we need a this pointer. The this pointer needs to point some address, so we cannot have a PR value of that, like just a literal. We have to store it somewhere in memory in order to have an address. Similarly, when we use arrays, like arrays really want to be pointers, so we need some storage. So whenever you have like an array PR value, it will be created in a temporary object. Interestingly, also when you like call a function that returns a PR value. For example, a function that returns a std string by value. When you call that and ignore the result, you will still need to run the destructor of the std string, otherwise you will have a memory leak. And to run the destructor, we need a this pointer. So the compiler will create a temporary object, initialize it with the result of the function call, and immediately destroy it. So what is the lifetime of a temporary? When the temporary is created, the lifetime starts immediately. Destruction happens after we've done evaluating the full expression, essentially at the semicolon. So we've got a function f, which contains a whole bunch of references, and then we're calling it with two PR values, 11 and the result of g, right? So two literal values. And because we bind those to references, we need to create temporary objects initialized to those references to make that work. And then while we're inside the body of f, the objects stay valid, so we can freely use the references, and they're only destroyed at the semicolon, so after we're done with f. Which is good. which means that if a function takes something by reference, it's always guaranteed that the argument stays valid throughout the entire execution of the function, but you have to be careful by taking its address and storing it somewhere else, because it could be a temporary that is then destroyed by that point. This is the basic rule. There are two exceptions, and those are called temporary lifetime extension. So the first happens when you bind a reference directly to a temporary. The lifetime of the temporary is extended to the lifetime of the reference. So here in the first line we create a temporary object because if you bind a reference to a to a PR value, and without lifetime extension, we would then reach the semicolon and immediately destroy the temporary object, and then we just have a dangling reference. This would be incredibly useless. So instead, lifetime extension kicks in, and the temporary is only destroyed when the reference goes out of scope. So throughout the entire execution of main, ref is valid and it can be used. While this seems nice, you have to be incredibly careful. It has to be a reference that directly binds to the PR value. So for example, getStrings returns a vector of string by value, which makes it a PR value. In the first line, we're binding the entire vector to a reference. Here, we're binding a reference directly to a PR value, so we get a temporary lifetime extension. We don't get it in the second line. This is because we're calling the subscript operator. And the subscript operator returns a reference. So in order to call the subscript operator, we do the temporary materialization, create a temporary object, call the subscript operator, and return a reference. This reference depends on the lifetime of the temporary object, but then the second line just initializes a reference based on another reference. At no point do we bind the reference directly to a PR value. Right? We just bind the reference to the reference returned by the square bracket operator, which could come from anywhere. Right? So we don't get temporary lifetime extension, and string immediately dangles and must not be used. So you really shouldn't rely on temporary lifetime extension, right? Because it's incredibly finicky and only works in a very specific use case. The second case for temporary lifetime extension is much nicer. When you do a range-based for loop, it might create some temporaries in order to call begin and end and so on. And all of those are destroyed at the end of the for loop. And this is the actual safe behavior. So this works. We're iterating over the entire vector. The temporary is destroyed after we're done with the for loop. But this one also works, because we create a temporary object in order to iterate it, and all temporary objects created while doing so are destroyed at the end of the for loop. So even though we don't do the other case of temporary lifetime extension, this one's actually safe. This is new in 23 or something, and I've been told not all compilers implement that, but I'm not talking about compilers, I'm talking about the standard, so I don't care about that. And it essentially means you don't have to worry when you do a range-based for loop. No matter how many temporaries are created, they're perfectly safe to use. Without this rule, the second line would essentially immediately dangle because we're iterating over something that's destroyed. But we're good here, this just works. Okay. Questions about temporary objects? Okay. So let's talk about placement new. An object is created by a new expression. There's a special kind of new expression, placement new. Placement new is an explicit constructor call. If you've got some memory, you can call placement new on that memory to create an object in that storage. Note that I'm using double colon and a void star. This is intentional because placement new can be overloaded. You can overload it for your own pointer types and in your own namespace. So if you don't call it all the time by casting to void star and using like the global scope, you might call a user-defined placement new that can do whatever. There is a standard library function, constructors, which just calls placement new for you in a safe way. But because it just would make some of the examples more bigger, so I'm not using that here. But like in actual code, you should use constructors instead of placement new in order to avoid the double colon and the static cast there. When we manually create an object by manually starting its lifetime, the compiler will not destroy it for us, so we also need to destroy it. And for that, we can manually call the destructor. The syntax for that is object dot tilde and then the name of the type. And due to some weird quirk of the grammar, the name of the type has to be an identifier. This means that t cannot be int, because int is a keyword. It also means that t cannot be stored string, because this isn't a single identifier. Right? But this is just a syntactic restriction. If you use, for example, a type def, you can always destroy an int. You just cannot write tilde int. You have to first write using my int equals int, and then you can write dot tilde my int. It's just a weird quirk of the grammar that it doesn't only allows an identifier. So instead, I am going to use std destroy at, which works for everything because here t is a template parameter, right? And the grammar allows that we can put t in there, even though if t is actually like an int, it's just a syntactic restriction, and it works out fine. So this actually destroys the destructor. C++ is such a weird language sometimes. But anyways. So now we've got some memory, and we can create objects in that memory. How do we get the memory? Right? How do we get memory that doesn't already contain objects? Right? We can use malloc. Malloc simply allocates storage. Then we've got a pointer to some storage, and then we can call placement new to start the lifetime, create objects, and move on with our lives. Right? We can then move it, use it, and in the end we have to destroy the lifetime, and then free the memory. Right? And so now we've got the full object lifecycle completely manual control. Right? We can decide when to allocate, when to start, when to end the lifetime, and when to deallocate. A more C++ version would be to use operator new. So again, you have to call it in global scope. It's just like malloc, it just allocates storage. Right? Start the lifetime, use it, destroy it, and then call operator delete to deallocate the storage. You can also use storage on the stack by using an array of unsigned chars.byte. So this allocates storage suitable, aligned, and big enough for it. We can then call placement new, remember the static cards, or use constructors in order to start the lifetime. We can use it, we can end the lifetime, and then it's deallocated automatically because it's like automatic storage. More interesting is this case. We can reuse the memory of an existing object. So we've got our int, allocated the storage, started the lifetime. We then destroy it. So now we've ended the lifetime of our int object, but we still have storage. And in the storage, we can create a new object, also an int, right? With a different value. We start an entirely new object that just happens to live at the same storage as our original one. We can then use that freely, and then something interesting happens at the closing brace, because we end the lifetime of which object exactly, the original x or the second one. We will get back to that later on. Now when you do that, you have to be incredibly careful. First of all, const means const. If you create a new object in a storage that is const, the behavior is undefined, right? So if you've got a const int, we destroy the lifetime, this is fine, right? The object is now destroyed. But when we placement new something in there, this is undefined behavior, because const means const. We cannot change the value of a const object. Const is const, mostly. Only for static thread automatic storage duration. So if you've got a constant on the heap, this is totally fine. Like we allocated a constant on the heap, we destroy it, and then we put something new in the place. Const on the heap doesn't mean anything, which is interesting. Also, the destructor still runs. The compiler doesn't care that we call destroy it. The compiler will still end the lifetime of the original object if it's responsible for that. So when we destroy, for example, string or the destructor, and then we don't put anything back in its place, the destructor will run again by the compiler, and we will have undefined behavior because we're destroying a string twice. So after we've called destroy it, you have to be really careful and put something back in there. Now this code works. We've got an int, we destroy it, we put something new in there, we use the new pointer. What happens if we now use the original object? Does this also work? Well, the answer is, it depends. So, if we do exactly that, after the lifetime of an object has ended, a new object is created at the same location, a pointer that pointed to the original object, a reference that referred to the original object, or the name of the original object will automatically refer to the new object if the original object is transparently replaceable by the new object. So when we've got transparent replacement, we're good. We can just use the old names, the old pointers, and the old references as if nothing has happened. And this is the definition. A is transparently replaceable by B if A and B use the same storage, which makes sense, and A if B have the same type. And then there are three edge cases. Const objects cannot be transparently replaced, base classes, and no unique address members. And then when we talk about sub-objects like member variables, it applies recursively to the parent object. So what this means is here we're okay. Like this is a transparent replacement because we're using the same storage and the same type, and we are not in one of those weird edge cases. Put a new int in there, we can just use the old name as if nothing has happened, because it will sort of automatically point to the new object. Which makes sense because it lives at the same address. This one is also potentially fine, right? If you do the assignment by calling the destructor and then calling placement new, this is transparent replacement if foo isn't like a no unique address member or base class of some other type. Right, so it's just a standalone object somewhere on the stack. This is totally fine. It's a transparent replacement. Nobody will even know that he did it. But you still shouldn't do it because foo could be like a base class, and then you're out of luck. similarly thing goes on for like, you can also do that with individual members. You're totally fine. Nobody will care. However, what's, for example, non-transparent is we've got our const int on the heap. We can do a placement new on it because const on the heap doesn't matter, but because it's a const object, this is a non-transparent replacement. So if we then use the old pointer, this is undefined behavior. And this makes sense because the compiler look at the first line and says, okay, so pointer points to a const object. This means that star pointer cannot change since it points to a const object. And so every time I see star pointer, I can just replace it with 11 because it's a const object, it cannot change. And then we change it. This is fine. It's just the compiler still assumes the star pointer is 11. And so on an optimizing compiler, depending on how well you hide the placement new, this can print 11. So this is undefined behavior. But what if you really want to do this for some reason? Is there any way you can continue using pointer? Well, you can use launder. So launder is a magic identity function. It takes a pointer and it returns the same pointer unchanged, but now it essentially forces the compiler to do reload. So if you launder a pointer, this is fine. It essentially means, hey, compiler, there might be like a new object at this place now, so forget everything you knew about the pointer and try again, right? And this makes it fine. And you can also use launder with references. So we've got a reference to the old object, we then destroy it, put a new one in its place. Reading the reference directly is undefined behavior because it's not automatically updated. But if we take the address of the reference, launder the pointer, and dereference it in it, this is then fine. So you can use launder to do like non-transparent replacement. Want to point out that like launder isn't like a magic get out of jail free card, right? It does not prevent undefined behavior in general, right? So we've got a float on the heap. We assume float and int are the same size. We destroy the float. We put a new int in this place. This is a non-transparent replacement because int and float are different types. So it's non-transparent. We can use the pointer return from placement new. We cannot return the pointer from f because we did a non-transparent replacement. And laundering doesn't help because we don't have a float, right? We have an int, right? Launder does a very specific thing. It does not magically make everything okay. This is still undefined behavior. So when do you need to use the launder? When you want to reuse the storage of const heap objects, remember, if then it's not on the heap, you can't replace it at all. Base classes are now unique address members. So never. We will get back to that later on. Questions about placement new? Okay. Yes. Every time you want to access the point, because otherwise the compiler doesn't know. What you can do is you can launder it, then reassign it back in a variable potentially, right? But yeah, like it's launder, not like mark as laundered or whatever, and then it implicitly changes things. Okay, so let's talk about implicit object creation. Another tautology. An object is created by an operation that implicitly creates objects, and the idea is code like this. This is like C like C++. We call malloc to get an int, we get a pointer, and then we assign it. And this really should not be undefined behavior, because this is how C works. But under all the rules we've discussed so far, this would be undefined behavior, because where's our int object? We've just allocated some storage. So where do we get the int, right? What makes this okay? And the standard essentially says, okay, don't worry. Some operations are specified as implicitly creating objects. And that means that if we are, like the compiler will implicitly create and start the lifetime of objects, if doing so would make the program have defined behavior. In other words, if it helps you, the compiler creates objects for you. This is, I think, the only instance where the compiler goes out of its way to prevent undefined behavior from occurring by implicitly doing something for you to make your code well-formed. So sometimes it will implicitly create an int for you in order to make your code well-formed. It's important to find out this only applies to types of implicit lifetime. This is the definition. It's a lot of words to say construction and destruction do nothing. As we will see, this makes sense because the compiler will not implicitly create an object if that calls some function, right? If it does something, if it not silently insert side effects. But it will implicitly create an int or any trivial struct. So when does it do that? Well, any allocation functions. So for example, std_malloc, operator new, allocator, allocate, and so on. They are specified as implicitly creating an object. And so when we do this line and we write star pointer equals 11, the compiler goes, this is undefined behavior, but I can implicitly create an int to make this okay. And so the compiler does it to prevent undefined behavior. Similarly, anything that starts the lifetime of an unsigned char.byte array. So here the compiler looks at this code and say, we're accessing an int, but we don't have an int, so let me implicitly create an int inside the buffer to make this well-formed. Except not quite, because there's a bug in the C++ standard. You technically have to use launder to make this well-formed. I don't really like that, because this is just clearly a wording issue in the standard. Let's pretend the launder isn't there. I still don't want to show you incorrect code, but like if this paper is merged, we don't need the launder. It's supposed to work. Otherwise, this rule is totally unnecessary. So ignore the launder. Similarly, memcopy and memmove. Right? So here we've got a char buffer. A char buffer is not an unsigned char.byte buffer, so this will not implicitly create objects. But when we memcopy the int in there, and then later need an int, the compiler will say, we did a memcopy can implicitly create objects, so let me create an int in there to make it well-formed. And again, the launder shouldn't really be necessary, it's just a bug in the standard. And then some set of like implementation-defined functions, like presumably mmap or virtual alloc, or some, I don't know, socket functions or whatever. They will implicitly create objects, just like the other way. Now, how does the compiler actually know to create an object, right? Like, at the time we're doing the mmap, it doesn't know that we need an object. Like, we could call placement new on the second line, and then we don't need the implicit object creation. So what the compiler is actually doing is using time travel. So here we've got a buffer, and then we roll a dice. And again, the launder is unnecessary. But like, if the dice roll is even, we require an int, and if the dice roll is odd, we require a float. So how this is specified is the first line doesn't do anything. We then roll the dice, discover that, this would be undefined behavior if we don't have an int. But I just created a buffer, so let me travel back in time, put an int in the buffer, and continue execution. Right? And it's important to point out the compiler only does it once. If we then later need a float, it will not do that and put a float in there, because it already puts an int in there. Like, there's always now an int. There always has been an int. Like, it just uses time travel to do that. Alternatively, you can see like quantum dynamics, say the buffer contains both an int or a float, and then when you observe it, it collapses and creates either an int or a float. This is also why implicit lifetime types cannot have anything do in the constructor, because time travel isn't actually implementable, and then you would have like different observable side effects that compiler writers probably wouldn't like that. So this is just like the abstract machine semantics require time travel at this point. On the actual CPU, they don't care about lifetime at all, so it doesn't actually do anything. It's just the wording is specified in such a way to make it well-formed. And again, just like launder, implicit object creation is not a UB prevention card. Like, this is an int, we reinterpret cast as a float, we launder it for good measure, because why not? This is still undefined behavior, because only the specified operations implicitly create an object, and here we don't do any of those, right? It's not the reinterpret cast that implicitly creates the objects, right? It's memory allocation, like buffer creation. So here, nothing will implicitly create a float object. This is just undefined behavior. The existence of implicit object creation means that code like this is potentially fine, but it might not be, right? Say we've got some trivial struct. This is an implicit lifetime type. And then we have some buffer, and we assume it's data in there. And if buffer came from one of those operations that implicitly create objects, we're good, right? As soon as we access it, the compiler will travel back in time to the operation to create a data object in there, and then we can read it. But if buffer came from some other operation, this might be undefined behavior, right? Because then the compiler has nothing to time travel back to in order to create our data object. So what we want is a way to like sort of explicitly do the implicit object creation. And you might say, okay, easy, just call placement new. Data doesn't have a constructor, so this doesn't change the bytes. I can just read the values, right? Because presumably those, like the buffer came from the network, and we want to actually read the bytes. But even though like data doesn't have a constructor that does anything, like logically, placement new creates an entirely new object with an entirely new value, right, that is completely disjoint from any bytes that were there before. So while this probably doesn't change the value, it's like semantically changes the value. So this doesn't do what you want. So instead we call another magic library function start lifetime s. And start lifetime s essentially says, hey, this is some buffer, please implicitly create an object of type data in there. It doesn't change the bytes, it just allows you to read the object as if it was always there. And there's also a version for arrays. And that way you can sort of explicitly create an object without actually changing the underlying storage. And while it is a magic standard library function, we can actually implement an approximation for it. So there's a start lifetime as, we take some pointer, and then we move the pointer size of t bytes to itself. This doesn't actually change the bytes, but memmove is one of those operations that implicitly creates objects. So if you then later need a t star, the compiler will travel back in time to the memmove to implicitly create the object. And that way we've got an object without actually touching the bytes. The standard library implementation is probably like some compiler built-in that also works with like const storage and is an actual no-op and not just a branch and then a no-op and things like that. But like in principle, it's implementable. So now we've got our objects. They are implicitly created. When are they destroyed? Well, objects are destroyed when we like the destructor calls, or when we release or reuse the storage. So what this means is that here we've got our int object. When we call placement new on it, we don't need the destroy at, because the reuse of the storage will end the lifetime of the original int object and start the lifetime of the new one. And this doesn't run the destructor. Similarly, when we've got an unsigned char buffer, this actually starts the lifetime of an unsigned char array. And then we then call placement new over it, we end the lifetime of that unsigned char array, and instead starts the lifetime of an int. And as a consequence, like memory leaks aren't undefined behavior. So we've got a string. And then we placement new a different string in it, without calling the destructor. This will end the lifetime without running the destructor. So the string will just leak. But this is perfectly fine, it's just a memory leak. Right? And then also when we do the closing brace, this will destroy the original string objects, but because of transfer and replacement, we're good there too. So we will just leak the original string in there because we implicitly ended the lifetime of the object by using the storage. So I'm assuming there are probably questions about this chapter now. Yeah. Yeah, so is it possible to query whether we've got an object at some location, essentially? No, because again, like the CPU doesn't care about object lifetime, so there is no data anywhere to indicate whether you've got an object. It's you know that you've got an object when you run your program and it doesn't do weird things that would indicate that you have undefined behavior. That's the only operation. Okay. Let's talk about provenance. So consider this code. We've got two objects, x and y. We set y to 11. Then we do something with the address of x, like pass it as a function, and then we return y. Every compiler is going to look at it and say, hey, y is 11, we return y. We don't change y in between, return 11. Right? This is a pretty basic optimization that compilers are expected to do. But what if this is the definition of do something? So do something goes ahead and takes the address, adds 1 to it, and sets that to 42. And let's say the stack is set up in such a way that this sort of, like even though we gave it x, like this reaches y, right? This changes y. Then the optimization would be invalid. So, okay, maybe we're just not allowed to like write do something like that, right? Because we don't know that pointer plus 1 points to y. But what if we do this? Now, whenever we call do something, x plus 1 is the address of y. So the dereference is always fine, right? Because it is the address of y, right? That's the same value. Like we've checked that before we call it. Is the compiler then still allowed to do the optimization? And if it like isn't, it's required to like know everything about all the functions that are called, which would be pretty bad. So, but the answer is yes, the compiler is allowed to do the optimization. So we're doing something wrong and do something. But how are we doing something wrong and do something since we just like explicitly checked that we've got the same address? And the answer is pointers aren't just addresses. Just because two pointers are equal doesn't mean they point to the same object. It matters how we got the object. And this is called provenance. So logically, again, like for the abstract machine, not for the actual CPU, a pointer has two things: the actual address and the provenance. The address is the thing that is physically observable. This is what equals equals compares. And then the provenance sort of identifies the object or allocation the pointer was derived from. So that remembers how we obtained that particular address. And the pointer dereference is only valid if the address matches like the range of allowed addresses for that particular provenance, and the current provenance at that address still matches the provenance of the pointer. And crucially, it doesn't matter how many pointer arithmetics or checks you do, you cannot change the pointer provenance. The pointer always remembers where it came from. So what's going on here is, even though like the address of x plus 1 matches the address of y, it's the same address, those two pointers have different provenances. And that means the out of bounds read is invalid because like pointer plus 1 is not in the allowable range of pointers derived from x. Right? It's just pointer. The pointer arithmetic is invalid because pointer remembers that it points to x, and at pointer plus 1 we no longer have x. It's essentially what's going on here, and this is what makes it undefined. Right? So the pointer arithmetic didn't change it. It's still a pointer to x, and now we're just out of bounds and aren't allowed to dereference it. And this enables the compiler to observe that nobody takes the address, like address y doesn't change by anything, and they can do the optimization. And if we attempt to change it, it is undefined behavior. And now we can also understand what's going on here. So we've got a const on the heap. This is some object with provenance a. We then destroy it and put a new object in there. And this is now has a different provenance. And so reading new pointer is fine, but reading star pointer is undefined behavior, because pointer has the provenance a, and we currently have an object of provenance b. Right? So the destruction and the placement new change the provenance at that location, which makes the old dereference invalid. And now we can also understand what launder is doing. It's an identity function for the address, but it updates the provenance. The resulting pointer will get the currently correct provenance for that particular address. Right? And this makes it fine. And the bottom point out that we cannot use launder type in the previous case, because the pointer, like the precondition is essentially that there was an object at that location sort of before, and we cannot use launder to make something out of bounds suddenly be valid and look at a different object. It just sort of is meant for this situation. And we can also now understand the difference between transparent and non-transparent replacement. If this were a transparent replacement, we wouldn't change the provenance. And then all the old names and identifiers and so on would still remain valid. But because it's non-transparent, we change the provenance, and we need to use launder to sort of get the current provenance. And provenance also applies to references. So this is the example of references, because the reference has the old provenance and not the new one. Directly reading it is undefined, but if we launder it, we get the new provenance and are free to use it. So every object has a unique provenance. All objects in an array have the same provenance. This allows us to do pointer arithmetic for arrays, right? But not for single objects. And then when you reuse the memory, this changes the provenance unless we do transparent replacement. And in that case, we can use .launder to update the provenance, but not in the out-of-bounds case. And this sort of explains a bit why like launder is an identity function. It doesn't do anything, but it actually does something. It's because like provenance isn't actually something the CPU cares about. It's purely something the standard talks about. And remember, just because two pointers are equal, they do not necessarily point to the same thing. Which is weird, but we want that, otherwise we wouldn't have any optimization going on. Questions about that? Yes? Yeah, I don't want to get into that. I don't know. So like conversion pointers to integers and then back to pointers is an entirely thing that, yeah, it's complicated. Yes.
Inside one storage,
right.
Like in one buffer,
yeah.
And plus one at the end. It's still valid, right?
Yes, yes. So you can do the comparison, like you can always write equals between any two pointers, right? But like provenance applies to dereference. And if you are within the same array, you can do pointer arithmetic, reach another sub-object of that array and dereference it because they have the same provenance. But if you sort of don't like cross in a different array, then it's also there is like it's not like directly. So if you, for example, have like an array of structs, and then all the structs have the same provenance, but if you've got a pointer to like some member of that struct, you cannot go back to the array based on that and do pointer arithmetic based on that, because the sort of like the provenance going the other way is different because it's not directly like a linear thing. Right? If that makes sense. If it doesn't, it's not. Don't worry. Right. Let's finally then look at type panning. So type panning, we've got some bytes they are stored in an object of type T1, and we want to interpret that as an object of type T2. And as you probably know, you just cannot, like reinterpret cast doesn't work. Right? So int and float, same size and alignment. We've got an int, we've got a pointer to an int, perfectly fine. We reinterpret cast that to a float and then dereference the float. The float dereference is undefined behavior because we do not have a float. We have an int, right? But the reinterpret cast is actually fine. So like colloquially, this is the strict aliasing rule, and like colloquially you say you can't reinterpret cast between unrelated types. This is actually like incorrect. The problem is the dereference. So the access is the undefined behavior, not the cast, right? You can't access an object to a pointer of an unrelated type. This is because in the general rule, like the type of a pointer or reference doesn't really matter until you access it. Right? You can freely reinterpret cast between different types, and you can store all your pointers as pointers to floats, right? If you feel like it, as long as you reinterpret cast back before access, you're all good. Somebody pointed out, or when you do pointer arithmetic, then you do the offset based on the type, but in other situations, like the type of the pointer, doesn't matter. Now, this is the strict aliasing rule. There are some exceptions. For example, you can, if you have an int, you can reinterpret cast it as an unsigned int, for some reason, and vice versa. And when we've got and you can also always reinterpret this as a char, unsigned char, or byte. And the idea behind the last one is it allows you to access the object representation, the sequence of bytes the object represents in memory. So we've got our int object, we obtain a pointer to byte, and then we can sort of iterate over the bytes that make up the int object and print the individual bytes, right? And this is well formed, in theory. In practice, this is undefined behavior because there's a bug in the standards. Because like some drive-by wording changes, essentially the problem is, like we're doing pointer arithmetic, but the standard doesn't say we've got an array of bytes, so the pointer arithmetic is undefined behavior. But this is like purely a technical thing, like it's meant to be well formed, it's just like somebody did some drive-by change to some wording and now this is accidentally undefined behavior. Yeah, don't worry about it. So we cannot use reinterpret cast to do type panning unless for those situations, and not even for this one, but ignore that. What we can do is, what we also can't do is placement new. Because like placement new again, like logically changes things. Right? This reads an indeterminate value. Which makes it, and then we also can't read even with the int because we no longer have an int, we reuse the storage, which ends the lifetime of the int, so this is undefined behavior. Now, if you do placement new like that, and then actually just like reuse the storage, going back to some earlier thing, this you have to then be careful of how you got the pointer, right? Because this code is actually undefined behavior. So we've got a float pointer that points to the address of the int, we then put a float in there, and then we dereference the float pointer. Even though we have a float at that address, and we have a pointer to float it, the provenance changed. Right? The float pointer logically is still a pointer to int. So the dereference still has the dereference of the int, which makes this undefined behavior. It also doesn't matter if we do it afterwards, right? This is still undefined behavior because the float pointer still points to an int. Even though it is a pointer to float, and we have a float at that address, it's still a pointer to int, right? Because the provenance didn't change. So you either have to use the pointer directly or launder it. But anyways, back to, we're trying to do type panning here, and placement new doesn't work because it changes the value, even when we do all the laundering correctly. Another detour apparently, I've moved some slides around at the end and I should have, anyways. This also applies to unsigned char, this behavior. If you've got a pointer to char and you then reinterpret cast it, this is still a pointer to an unsigned char buffer. This isn't a pointer to an int. This is the bug in the standard. This is why you need launder. Right? There's a paper that says in one of those situations you don't need launder. But this is why you currently need launder because the int pointer logically is still a pointer to unsigned char. And this means that this is the final use case for launder when you want to reuse memory as storage for a different type. Which means never, but there are some terms and conditions. Anyways, sorry about the slight detour. Back to type panning. We can use type panning with start lifetime math, which is unusual, but it works. Right? So we've got our int. We start the lifetime of a float. This doesn't change the bytes. It ends the lifetime of the int object, start the lifetime of the float object, and now we can read it as a float. We just no longer have an int. Right? if we want an int, we have to start an int back. But then because we did like provenance changes, we're now at like provenance C and not provenance A, right? So we've got provenance A, but then we start a float with provenance B, and then when we start another int, even though we're like transitively back to int, like we at provenance C and no longer provenance A, so the I is undefined behavior, you have to launder it. But like in principle, this works. Like this is type punning, in a really weird way. So how do we actually do type punning? Well, we can use memcopy. So we've got an int, we've got a float, we copy the bytes over. The good news here is this doesn't interact with object lifetime rules at all, right? We've got an int object, we've got a completely separate float object, and then we just copy the bytes over. So afterwards, we still have a float and an int object because we didn't touch the lifetime of anything, we just copied bytes. The fancy C++ version. Oh, I pressed the button, and now I've got. Okay. Apparently I have a button to hide, like, turn off the projector, but I don't have a button to turn back on the. So. You never learn. I have this thing for like 8 years. Never pressed that button. Okay. Right. So the C++ version of memcopy is bitcast. Bitcast is essentially memcopy that works at compile time. It's also like a compiler built in, so you like optimized out the actual copy operation, and it's just a register thing. Like it does actual type punning at the CPU, but like logically they're different objects. So this is how you can do type punning. You can also do type punning in a very specific situation with reinterpret cast. So we've got a struct A that contains an int member. And then we can reinterpret cast that struct A to an int pointer and use that because this now refers to the pointer of the first member. And then also when we have a pointer to the first member, we reinterpret cast it back to the struct. And this exception is explained in the pointer interconvertible rules. So when your two objects are pointer interconvertible, then they have the same address, and you can just reinterpret cast to go between one and the other. And then, like in the following situations, when they are the same objects, then they're obviously interconvertible. When one is a union and the other is a member of the union, so we can get from a union member to a union. Or in the previous example, we've got the standard layout class object, and one is the first non-static data member. And then we convert a pointer to a class to a pointer to the first member, and a pointer to the first member back to the pointer to the class. Right? This is similar how you convert a pointer to a base class, right? But just for the first member in standard layout class. And bonus points in the case with the unsigned char buffer where we need launder, the paper just adds another clause here where it says that an unsigned char buffer is interconvertible with objects inside it, and this makes it okay. It's just missing the clause there. And so in code like this, when we've got a standard layout struct, we've got a member of the first thing, we can reinterpret cast between them. This does. Right, and this also doesn't like affect the lifetimes of objects or anything. It's just we've got an A object, it has an in sub object, and they just happen to have the same address, and we can just convert between pointers between them. Right, this doesn't really do type punning. It also only applies to the first member. So if you've got another int, you cannot do pointer arithmetic to get to the first int and then reinterpret cast it, because then we've got the provenance problems again. Right? So it's a very specific situation that's probably there for some use case. And finally, the last case where we got object is when we implicitly create the active member of a union, which means type punning by a union also doesn't work. Union, int, and float. Initialize the float, assign the int, initialize to int, assign the float. Reading the float is okay, because this assignment creates the float object at that address and destroys the int. So when we read the int, we've got undefined behavior because we don't have an int object, we have a float. Right? Changing the active member of a union implicitly like destroys the old object and creates a new one in the space, which means that type punning via union also does not work. So if you want to do type punning, you have to use bitcast or memcopy, because all other situations implicitly ended the lifetime or never started the lifetime of the original thing. It wouldn't be C++ if there weren't exceptions, so there's another exception for this case, the common initial sequence. So if you've got two types and they both start with an int, for example, you're permitted to read that int to either member in a union. This is the wording, this is the code. So, union U, struct A, struct B, both start with an int. Right? Then we initialize the A object and read the prefix from the A object. This is fine because the A object is valid anyway, right? It's the active one, that's good. But the second line is also fine, right? Even though we're accessing the B object, we're only accessing members that are part of the A object anyway, right? And so essentially what's going on here is the compiler will at runtime rewrite the access to refer to the currently active one. And then the u.b.prefix means the same as u.a.prefix, and we just read the a object, right? Because they both start with the same one. And as I said, this doesn't change the lifetime of anything. The compiler just does the correct access for you, which I guess makes it the second situation where the compiler helps you avoid undefined behavior. Okay. And with that, I think, yeah, I won't have time to do into the other thing. So with that, I'm done. I want to end some guidelines. Don't rely on implicit object creation, right? It's like really weird, really finicky. Explicitly use placement new if you want to start inside a new object, or call start lifetime s if you've got some bytes and you want to say there's an int in there, please give me that int, right? So if you read some bytes from the network, call start lifetime s directly into your struct, and then you're good. Whenever possible, like placement new and start lifetime s give you pointer. Use those pointers, right? Then you don't have to worry about launder at all, right? If you directly just use the pointer from placement new and ignore all the old pointers, then you're good. You don't have to worry about it. And use unions instead of unsigned char buffer. Because for unsigned char buffer, if you got the reinterpret cast, you potentially need to use launder depending on when this paper lands and how strict you want to avoid undefined behavior. That's really undefined behavior because the standard has a bug and not because we intended it to be this way. Just use unions, right? They work in Kongsberg more easily. It's just nicer, so you don't have to deal with this. And with that, how do I get to the last slide now? This? Okay. Okay, sorry. I'm too afraid to press shortcuts again. So, I work at ThinkCell. We're hiring. You don't need to know all the details about object lifetime, but if you're interested. I've also got some socks, the L value, R value socks. You will find them by the slide where you put in the, vote on how good the talk was, and I also have some more here. So keep that in mind when you. Anyways, thank you. Are there any other questions? Yes. Yeah.